Okay, so this online lecture is meant to be a review for just using Newton's second law to solve some of the basic kinds of mechanics problems that we're going to encounter in this course. So this is not going to be one of the hardest problems that we cover, but I just thought it would be useful for you to review this to make sure you're up to speed with just using the basic Newton's second law. Okay, so the problem that I'm going to do, the example problem that I'm going to do is based on, it's very similar to problem 138 in the book. So and the problem is really, it's about, if you imagine having a tilted plane and a small puck or a small block or of some sort that's able to slide on this tilted plane. We're trying to figure out the trajectory of this sliding piece of stuff. So let's say puck on tilted plane. Okay, so you could imagine a picture like this where you have some sort of floor that's horizontal and the tilted plane that is sort of something like this, where there's an angle theta that defines how much tilt there is to this plane, and then resting on the surface of this plane is a puck. So that's this thing here. Okay, and let's define the coordinates that we're going to use for this problem. So we'll define the axes so that the y direction is parallel to this plane. The x direction is sticking out of the chalkboard or this whiteboard as I've drawn it here. And the z direction then is perpendicular to the y direction and the x direction and perpendicular to the surface of this plane. Okay, and I'm going to draw this from one more angle. So if you imagine that you're looking straight down at this from above, so if you're looking straight down at this plane along the z-axis, let's call this view A. So view A of this situation looks just, this is just looking directly at this tilted plane, and then the y direction points that way and the x direction points this way. Okay? Okay, so the only forces that we need to worry about, okay, so that's the next question we should ask. What are the forces acting on the puck? So the forces that are acting on the puck, if you examine the situation, are gravity. So gravity is pulling straight down as usual. So if the mass of the puck is m, then we have the gravitational force mg pointing straight downward towards this floor down here. And then there will also be some normal force that keeps the puck from going through the board, right? The board itself exerts some force on the puck that is in this direction, in the z direction. So let's say this is the normal force N. Okay, and to get, let's take a little bit more of a detailed look at the forces. So if this is the plane and this is the puck, and you have the gravitational force that's straight downward, we need to break this into components. So there's two components. There's the y component of the gravitational force, and then there's a z component of the gravitational force. So let's say that if this is F, then this is F sub z and this one is F sub y. So the y component of force is the one that actually pulls the puck down the plane, and the z component of the force is going to be balanced by the normal force. So that is to say, N is going to be equal in magnitude to Fz. Otherwise, the puck would be leaving the surface of the plane. Okay, so these two forces balance each other, so they don't cause any motion, whereas this F sub y, that y component of the gravitational force, again that has magnitude mg, is going to be pulling the puck down the plane. All right, and the angle theta here, which determines the tilt of this plane, is also the same as this angle. If you think about the geometry for a minute, you can convince yourself that this angle is theta. It's the same as this angle theta. All right, so if you then look at this, then this y component here, you can put Fy right here if you wanted to redraw it. So Fy is equal to mg sine theta in magnitude. So that's the magnitude of this y component Fy, the gravitational force. And okay, so this is our force diagram, and this is important for when we move forward here. So okay, what's our goal? Let's at least write this down once. So the goal is going to be to calculate the puck's trajectory. All right, that's our goal, and we'll assume some givens in the problem, some initial conditions. Let's assume that initially at time 0, that the position is, say, here. So we'll put the position here at time 0, and let's say that is the x position equals 0, and the y position equals some initial value y naught, y sub 0, y naught. And let's also assume that the x component of the puck's velocity is not 0. Let's say that's so. This thing initially has a velocity that's in the x direction only, so that it has zero component of velocity in the y direction initially. Again, these are just the initial conditions here. Okay, so our goal is, given these initial conditions, to figure out where does the puck go. And I think by your intuition, you know that the gravity is pulling the puck down the plane, that is down the plane this way, so the trajectory is going to do something like this, right? So we need to calculate to determine what is the shape of that line, in a way. And what we're actually going to calculate is x as a function of time, the position. We're going to calculate the position x as a function of time and the position y as a function of time, the two coordinates of position as a function of time. Okay, so the first step, after just examining the forces and looking at the initial conditions, the first step is to write down Newton's second law. So which says that, I'm going to write this down in vector form first, that is the total forces F acting on the puck are equal to the mass times the acceleration of the puck. That's Newton's second law, of course. Okay, now if we then break this into components, then we have that the x component equals the x acceleration, the y component equals the y acceleration, and so on. So if we can figure out what are the x, y, and z components of the forces acting on the puck, then we will have our equations of motion that which we will then solve to get the puck trajectory. Okay, so as we already looked at here, the sum total forces in the z direction is 0 because the normal force cancels Fz, and there are no forces in the x direction at all. The only remaining force to worry about is the y component of the gravitational force. So this equation, the x equation, becomes 0 equals mx double dot. So that's the same for the z equation. And the y equation is the slightly more interesting one. That's going to have a minus mg sine theta equals my double dot. Why did this minus sign show up? The minus sign comes from the fact that, remember, we defined the y direction as pointing up the slope. Therefore, in Fy, this y component of the gravitational force pointing in the opposite direction gives it a minus sign. Okay, so we can go ahead and then do some simplification here, and we have then this differential equation. We have the second time derivative of the y component of position is just minus g sine theta. So we just have to solve this and these, I suppose, if we're going to figure out the trajectory of the puck. Okay, so let's make some more space here. And all right, so I'm going to rewrite this equation and we'll solve it up here. Okay, so how do we solve this? This is a very simple differential equation. Some differential equations are easy to solve, some are hard. In this case, it's fairly easy to solve because this is just the y acceleration is a constant. Keep in mind that theta is a constant, it doesn't change with time. G is a constant, it doesn't change with time. So this is just y double dot equals a constant. So the way to solve that is you could think of it like this. You could say this is one time derivative of y dot equals this constant. And then if you move, oops, that's supposed to be a dt. That's a time derivative of y dot gives you y double dot. So then if you move the dt to the right-hand side, and you leave the dy dot on the left-hand side, then you integrate both sides. You integrate just dy dot and leaves you with just y dot. If you integrate this side with respect to time, then you get minus g sine theta t and plus some constant of integration. We'll call it c1 here. This side also would have a constant of integration, but if you combine them together into one single constant, it simplifies things a bit. Okay, then we're still not there. Eventually we're trying to get y as a function of t, not y dot as a function of t. This one is useful. This tells you that the y component of velocity follows this equation, follows this as a function of time. But we want to go further and get y as a function of time. Okay, so this will take a similar step of integration. We realize that y dot is just dy dt. C1 there. and then we're going to move the dt to the right-hand side and integrate again. So we'll have an integral of dy on the left-hand side, integral of minus g sine theta t plus c1 dt on the right-hand side. Okay, so then the left-hand side integrates to be just y. The right-hand side integrates to be minus g sine theta t squared over 2, right? That's what you get when you integrate t with respect to time. And c1 times t, and then plus some constant of integration again. And just to, if you want to, you can always go backwards to verify that your integration worked properly by integrating this, or sorry, taking a derivative of this. If you take a derivative of this, right-hand side here, you will get the integrand here. This. Okay, so that is a solution to the y component of motion. The only thing we need to do still is to use our initial conditions that we were given at the beginning. The initial conditions said that at time 0, so y at t equals 0 was 0. We start out, no, sorry, was equal to, not 0, it was equal to y naught. It was equal to this distance, y naught. Okay, so if you plug that in, if you plug in t equal to 0 here, that tells you that C2 has to be equal to y naught, right? If you plug in t equals to 0, that kills this term and this term. So it says that y naught equals C2 at time equals 0. And our other initial condition was that that the initial component of y velocity, that is y dot at t equal to 0, was 0. That is, it was initially at rest. And here's our y dot equation. So if you use this condition on this equation, it says that at time equal to 0, c1, so this term is 0 at t equal to 0, and so y dot equals 0, so c1 must be equal to 0. Okay, so there you have it. That is, you have an equation that determines the y-coordinate and how it progresses as a function of time. That is, I'm going to plug in these constants here and show you this is the final form of an answer. How does y depend on time? It's y naught, that's the C2, minus g sine theta t squared over 2. Again, this term is 0 because C1 is 0. So that's it. That's the y solution. This is how y depends on time. And you can easily do a similar sort of solving of the x equation. It has different initial conditions, and you will get to a solution for the x as a function of time by integrating in a similar way to what we did with y. And I'm going to leave that for you to figure out.